Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 8th episode in a series that seeks to demystify programming in assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel. Don't forget to subscribe and click the bell for notifications while you're there so that you'll know when the next episodes come out. And start this playlist from the beginning. So far in the series, we have learned the fundamentals of assembly programming by going through the entire 65C02 instruction set and examining how each instruction works. But programming is a lot more than just knowing all the instructions. You need to know how to get the whole computer system to do what you want, and with the X16, that starts with the kernel. No, not that kernel. We're talking about the application programming interface of the X16 system kernel. And that's kernel with an A. You may be familiar with the concept of a modern operating system kernel like Linux, but this is a bit different than that. The X16 doesn't have an operating system in the modern sense, just some software that runs from a built-in ROM to provide a simplified way of interacting with the hardware. You're already familiar with the BASIC interpreter, which is what the system boots to, and is the general operating environment for the X16, just as it was for most 8-bit home computers. Underneath BASIC, there is the kernel, which is used for accessing the screen, keyboard, storage, and communications. If you are writing your software in assembly language, you have to access the same low-level kernel subroutines that the BASIC interpreter itself does. We've already seen how a couple of the kernel subroutines work, and how they are based on the Commodore kernel subroutines down to their addresses, interfaces, and behavior. The X16 kernel recreates most of the Commodore 64 kernel, with some additional subroutines that were added for the Commodore 128, and places some of the basic drawing features of the GEOS graphical user interface right into the ROM to be generally available. As ROM is read-only memory, the kernel is always available and can't be overwritten at any time. However, certain subroutines go through a RAM vector which can be replaced at runtime to change their behavior until the original vectors are restored or the system is reset. As a quick refresher, let's take another look at the X16 memory map. As you can see here, ROM starts at hex C000 and goes all the way to the end of memory, meaning that the last 16 kilobytes of memory is strictly read-only. However, that doesn't mean it never changes. This 16K is banked, so the data there changes based on what the currently selected bank is. To run a kernel subroutine, ROM bank 0 needs to be selected, but we can usually assume the currently selected bank will work. But how does that work? All of the kernel code is in bank 0, but the subroutine addresses are all past hex FE00, so it's pretty easy to deduce that all the code for the subroutines don't immediately follow those addresses. There just isn't enough room in those last 512 bytes for a few dozen subroutines. But there is enough for a jump table, and that's what the end of ROM bank 0 is. In fact, even though bank 4 has BASIC in it and bank 5 has the machine code monitor, there is enough room for those to have the same jump tables in them, along with some bridge code to switch to bank 0 and run the intended kernel subroutine. Generally, most programs aren't going to switch to those other banks at all, and if they do, only for the time needed to access their data before switching back to 0 or 4. We can do this by writing the desired bank number to the ROM bank register, which is at hex 9F60 in the current emulator, but the X16 hardware will ultimately use the 0-page address 01. The first kernel subroutine we saw in this series was CHAROUT, or character output. As seen in our earlier examples, the address is hex FFD2, so we do a JSR FFD2 to run it. But if we were to actually look at ROM bank 0 at FFD2, we would see an indirect jumps to an address stored in RAM, specifically at hex 0326. There is yet another ROM address stored there, and that's where the actual subroutine starts executing, eventually reaching an RTS to return us back. This same mechanic existed with the original Commodore 64, and you could overwrite that address at 0326 to point to your own code to make CHAROUT work differently. But if you left that vector alone, the default behavior would happen, which is to send the character code in the accumulator to the default output. The initial default output is the screen, of course, so we will see that code take effect at the current cursor. If it's a control code, its effect will happen. If it's a visible character, its glyph will be drawn to the screen at that cursor, and the cursor will advance to the next position. When we get into how the Vera video system works, we'll learn more about things like screen codes and tile maps, but for now we can take for granted that characters will get printed just as if we typed them. CHROUT can also be used for writing to a file, but we'll get into that in a later episode as well. What's important to understand for now is that the call to CHROUT will not effectively change the contents of any registers, so the code you put in A will still be there when it returns, and any values you had in X and Y will still be there too, thanks to CHROUT storing those values on the stack to be pulled back to the registers before it returns. Not all kernel subroutines do this, and each slide will point out which registers may be affected by calling them. Now that I've introduced the possibility of changing the behavior of CHROUT, naturally we're going to want to see how to hack it. Here we are going to make it so that CHROUT always outputs either a control code or a graphical character, no numbers or letters. So let's start by setting up constants for the ROM bank register and the CHROUT address, and then a zero-page address to store a pointer we can use to dereference the RAM vector. Then we allocate a couple bytes of RAM to store the original CHROUT vector so we don't have to rewrite the whole subroutine. At start, we set the ROM bank to 0 and copy the address of the RAM vector to our zero-page pointer. We could have used the immediate documented address of 0326, but here we don't need to hard code an additional magic number. We already have the CHROUT address, which we know is going to point to an indirect jump, so we can just pull that address right out of the ROM instruction. The byte at the CHROUT address will be the indirect jump opcode, so CHROUT plus 1 will be the low byte of the address operand, and CHROUT 2 will be the high byte, so we can get those with some absolute loads instead. With that address copied to the 0 page, we can now do an indirect load to get the low byte of the destination address, which we can store as the first byte at CHROUT vector. To get the high byte, we load y with the value 1 so that we can do an indirect indexed with y load, and then store that in the second byte of CHROUT vector. With the original destination safely stored in a new RAM vector, we can overwrite the original RAM vector to point to new code. We're going to define a new entry point labeled graphout, so we're going to store that address using the same addressing of the zero-page pointer we set up earlier, which means that 0326 will contain a RAM address now, and that's what will get called indirectly at the start of CHROUT. Now, we define graphout by comparing the character code in A with hex 20. If it's less than that, it's a control code, so we branch right to @done. If it's hex 20 or greater, we compare it again to hex 60. If it's greater than or equal to that, we'll branch to @done now. Otherwise, we know the code is between hex 20 and 5F, meaning that it could be a number or letter, but definitely a visible character. So we OR it with hex 80, which will set the high bit, forcing it to the range of hex A0 to DF, which are all graphical characters. Then we finally fall to @done, where we do an indirect jump to the original vector that we stored earlier in CHROUT vector. This will take us back to ROM, and the original CHROUT subroutine will execute with a modified code in A and eventually return as normal. Then we have a new starting point for our code that can take advantage of our hacked kernel. We load the accumulator with the Petsky code for the letter A, which is hex 41, just like capital A in ASCII or Unicode. Then we call CHROUT to print not an A, but the hex code C1, which is a spade symbol, which is what you will see if you hold down the Shift key while typing A. Yeah, that's not a coincidence. Okay, enough hacking for now. Let's get back to the kernel as it exists normally. The other kernel subroutine we've seen is CHRIN, or character input. It is the basis of the basic line editor, so if you are familiar with Commodore BASIC, you should have a feeling of how this works. It starts blinking the cursor at the current position and then responds to the keyboard by writing characters to the screen or processing the keystrokes as control codes. The character glyphs will remain on screen as typed, but after the return key is pressed, The subroutine returns and places the PETSCII code of the first character typed into the accumulator. Subsequent calls will return immediately with the rest of the characters in the line buffer until the return character is reached at the end of the line. When CHRIN returns the return character, we know that the line buffer has been cleared, and the next call to CHRIN will enable the cursor again and fill up a new line buffer. CHRIN can also read a byte from a file if it is open as the default input, and then it no longer uses the line buffer. We'll see how that works in a later episode and how to use the carry bit to determine whether the read was successful. For now, we are just going to deal with the keyboard input, and just be aware that the X and Y registers may also be modified by a call to CHRIN. Similar to CHRIN is a subroutine we haven't seen before called GETIN, or GetInput. It does not use the line buffer, but instead uses the keyboard buffer. As the user types on the keyboard, the codes get placed in the buffer waiting to get processed. The CHRIN subroutine does this immediately during its initial call, where it is constantly checking for the return key to get pressed. The rest of the time, the keyboard buffer fills up until GETIN is called. Like when CHRIN is getting input from a file, GETIN returns immediately with the oldest code in the keyboard buffer and puts it in the accumulator. If the buffer is empty, it returns 0. GETIN can also work with files that are open as the default input, in which case it works exactly the same as CHRIN, including using the carry bit to indicate any errors or the end of a file. Let's take a closer look at how the keyboard buffer works, as that is usually a better way to handle keyboard interaction instead of the basic line editor. We're going to write a little snippet that will get the first key code entered, whether that is already sitting in the keyboard buffer or the buffer is empty and we are waiting for the next keystroke. We'll take that code and put it in a 0-page variable for later use, then flush out any other codes that may be sitting in the buffer before moving on. The keyboard buffer is filled during interrupts, so new codes could show up in the middle of one of our loops if the user is a fast and/or sloppy typist. To do this, we first define the addresses for GETIN and the 0-page variable we want to use, which we are calling keycode. Then we start our wait loop to keep checking the keyboard buffer until a non-zero code shows up. Once our call to GETIN finally puts a non-zero value into A, we store it to keycode. Then we go into our flush loop to keep calling GETIN until it returns 0. Then we know the buffer is completely empty before we move on. Then we'll know the next time we call GETIN, it won't have any stale codes left over, only what was typed after this flush completes. Often it's a good idea to do a flush like this at the beginning of your program as well, if you're going to be using GETIN later. Next we're going to look at another new subroutine called SCREEN. If you're already familiar with X16 Basic, this may be a bit confusing, as this has nothing to do with the basic screen command, which modifies the display properties to select different screen modes. This simply reads the current state of the display properties and returns the current screen dimensions in terms of the number of characters that are visible in each row and column. At startup, the X16 is an 80-column mode with 60 rows of text visible. Since the character glyph tiles are 8 by 8 pixel squares, that means the default resolution is 640 by 480. So when you call the screen subroutine before changing any display configuration, it will load X with 80 and Y with 60. You could then use that information to determine how you want to format any text or tile output, or trigger a change to the display settings to get the dimensions to something more useful. You may also notice that this is the first subroutine in this lesson that doesn't have a RAM vector listed. That's because it doesn't have one, so there is no way to change screen's behavior. The most direct use of screen would be to calculate a new cursor position, which you can set with the plot subroutine. You can also use plot to get the current cursor position as well. You can control the behavior of plot using the carry bit. A CLC before the call will clear C and have plot move the cursor. Counterintuitively, you place the X position in Y and vice versa. The coordinates are 0-based, with 0, 0 being the upper left corner. The maximum values will be 1 less than what is returned by screen, so the default bottom right corner would need 59 loaded into X and 79 loaded into Y. If you do an SEC beforehand, the C bit will be set and the plot will ignore any values loaded into X and Y and just overwrite them with the current cursor coordinates, again opposite of what you would expect. X will be loaded with the Y coordinate and vice versa. In either case, the values in X and Y may change after the call, so that needs to be considered. The simplest and fastest way to load data from a file is to do it all at once using the load subroutine, which is at the heart of the basic load command. But unlike basic, the kernel load requires you to use some helper subroutines before it is ready to work. To illustrate this, we are going to look at a typical process for using load, first by allocating space in RAM to receive the data. It is extremely important that the allocated space is large enough to take all the data from the file. Otherwise, the file data will spill out of it, overwriting other data or code in RAM. For this case, we are going to assume that the file foo.bin is no larger than 2000 bytes, so we allocate a 2000 byte file buffer after defining the addresses of the kernel subroutines we'll need. We also need to allocate a string holding the file name, and with CA65 you need to specify that with lowercase letters, even though the actual file name will be in all caps, which should generally be the case for any file that will be accessed by the X16. We define a subroutine called loadFile, and the first thing we do is call the SETLFS kernel subroutine with the registers loaded with some magic numbers. We'll get to those soon. Moving on, we call the SETNAME subroutine to set the file name with some new register values. In A, we load the file name length by calculating it in the assembler, using the load file label as it is placed right after the file name buffer. And we can just subtract the file name label to get the length. Then in X and Y, we load the file name address with the low byte in X and the high byte in Y. And we'll see X and Y used like this in several kernel subroutines that need addresses as input. Finally, we do the load itself by first loading 0 into A to indicate CPU RAM, and then put the file buffer address in X and Y as the place to start loading the data. Let's go back to that mysterious SETLFS subroutine. It stands for Set Logical File Settings, and the registers set up 3 specific values that are needed to determine how the file is going to be accessed. You need to load A with a logical number, which can be used to differentiate between multiple files that may be opened at once. However, if you are just loading or saving one file at a time, you can just load A with 1, like we did earlier. X needs to be loaded with the device number, and for that you are usually going to use 8, which specifies the SD card interface on the X16. On the emulator, if no SD card image is specified, device 8 will be the host file system. We've been using that all along in this series because the basic load command uses device 8 by default, and we haven't been dealing with any SD card images. Finally, Y needs to be loaded with something called the secondary address, or SA for short. If you load this with 0, as we did earlier, it will let you specify a load address in the code, using the X and Y registers before calling load. If you set SA to a non-zero value, load will ignore X and Y and just use the 2-byte header in the file to determine the load address. As we saw way back in the first video, the PRG files we generate with the linker start with a header specifying the hex address 0801. That's why we don't specify a load address when loading the PRG files from BASIC. They will automatically get loaded to the correct address based on their 2-byte header. You can do the same thing with data files by specifying that their load address is in their headers, but that won't stop a program from setting SA to 0 and loading the file to a different address. SETNAME, of course, stands for Set File Name, and we just saw exactly how that works. A needs to be loaded with the length of the file name, then X and Y need to be loaded with the address of the file name in memory. This will associate the specified file name with the logical files set up by the most recent call to SETLFS, which should then carry through to the next load call. Load will finally load this file specified by SETLFS and SETNAME into RAM, all at once. A needs to be loaded with 0 to load it into CPU RAM. You can load A with 2 or 3 to load the data into a bank of the Vera video RAM, but we'll see how that works in a later episode. If SA was set to 0 by SETLFS, X and Y need to be loaded with a valid RAM address that can take the entire contents of the file without overwriting anything it shouldn't. If SA was set to a non-zero value, X and Y will be ignored, and load will just use the 2-byte file header to determine where to load the data. Please note that even if SA was set to 0, load expects the header to still be there, so the data that will be loaded will always start with the 3rd byte of the file. After load returns, the C bit will be set if there was an error, and then A will be loaded with an error code. X and Y will also be changed to the address of the last byte that was written to RAM. This can also be a good check to make sure that the ending address was still in the allocated buffer and nothing else was overwritten. Now we're going back to that last code we saw to modify it for saving data to a file instead of loading it. Again, we define the addresses of SETLFS and SETNAME in addition to save, but then we also need to set up a couple bytes on the 0 page to store a 16-bit address. We go through the SETLFS and SETNAME, same as for load, but then we have to do a little setup before calling the save subroutine. We need to store the address of the file buffer in the 0 page pointer we defined, and then store that 0 page pointer address in A. Then we need to store the address of the byte that follows the last byte we want to save in X and Y. In this case, we just let the assembler calculate it by adding the buffer length to the start address. Now, we can finally call save and all the data will be saved to the file. So let's take a closer look at save. Like load, it is also at the heart of the basic command with the same name. Since it needs 2 16-bit addresses as input, it requires the use of a 0 page pointer whose address is only 8 bytes and can be loaded into the accumulator, which save will use to get the starting address back off the 0 page. Then X and Y need to be loaded with not the ending address, but the address after that, so that the difference between the two addresses is the total number of bytes that will be written to the file. If the save was successful, the carry bit will be clear when it returns. Otherwise, C is set and an error code will be loaded into A. The file that is written will replace any file that already exists with the same name. Data will not be appended or overwrite a portion of the old file. An entirely new file will be created with a 2-byte header containing the original starting address that was put in the 0 page pointer. That way, you can load the data back to the same address later without having to specify a starting address in the code, or just by doing a load from the basic prompt. For this episode, we're going to stop trying to get all the example program code into slides and just examine it right in the text editor. But first, let's take a look at what this program is going to do. We're going to use all the subroutines we learned about today to make a simple program that interacts with a screen, the keyboard, and a file. First, it will change the screen mode to be 40 by 30 characters to make it easier to see. Then, it will place the letters A, B, and C with colons on the screen. If the user presses one of those letters, the cursor will appear on the screen next to that letter and let the user input a line of text. When the user hits return, the first 10 characters from the line buffer will stay there. When the user presses Q, the 3 10-character strings are saved to a file named ABC, and the program quits. The next time someone runs that program, the ABC file will be present, and its contents will be displayed to the screen at the beginning, and the user can change any of them before saving and quitting again. So let's take a look at how we can code that. Of course, we start with the segment preamble and then our constants. We're going to need a 0 page pointer for save, the addresses of all the kernel subroutines we're going to use, then a couple of Vera register addresses that we'll need, some Petsky codes we'll need, and finally just some constants specific for our program. We need the magic number to write to those Vera registers to go into 2x zooming, and then the size of the strings we'll be dealing with. After that, we see a macro called printline. A macro is like a function in a high-level language, except that the code is inserted everywhere it gets called with the argument values replacing the argument names inside the macro. It is faster than a subroutine and provides a simpler syntax, but requires more memory to store the code as it gets repeated as many times as it gets called, rather than just existing in one place. So generally, it's a good idea to make macros relatively small, and we'll get into them more in a later episode. Here we want the macro to have 3 arguments that will tell us which row the line is in, which letter it starts with, and the address that contains its string. First, we want to get the cursor in position, so we clear C and put the row and column values into X and Y, then call plot. As you can see, we take the row value from the argument, but the column will always be 5. Then we want to print out the letter from the argument, followed by a colon and then a space, all using carout as we have seen before. Then we print out the string using X to index into the address from the last argument. Once we have printed out all 10 characters in the string, we fall out of the loop and the macro is done. We'll see how to use this later, but for now we need to start our actual code. We have the customary jump start, followed by the data we need in RAM, starting with the file name. Again, we use lowercase letters for the file name in the assembly code, but the actual file name will have uppercase characters to be compatible with the X16. Then we put in the end file name label to make it easier to find the end of the file name string. After that, we have the 3 strings we are going to edit initialized to all spaces, and then another extra label for the address after the last one to use for saving the data. Finally, we get to start and we call screen to see what the current dimensions are. If the width isn't 40, we will store that magic number into the Vera register DCH scale, which controls the horizontal scale of the display. By default, the value here is 128, which means a full 640 pixels wide. Setting it to 64 will effectively zoom to the left half of the screen, meaning that it will now be 320 pixels or 40 characters across. We then do something similar with the height, making sure it's 30, then forcing DCV scale to 64 if it's not, which will similarly zoom to the upper half of the display. After that, the display will be 240 pixels or 30 characters high, and everything will finally be zoomed in 2 times. We'll look into more Vera registers in a later episode, but these 2 are pretty simple to use. And for most graphical programs, you'll want to do this 2x zoom by just writing 64 to both registers at the very beginning. Then we go through that process of loading the ABC file just as we saw earlier, using that end file name label to let the assembler calculate the string length, and then the A string address as the point for loading the data from the file. If the file doesn't exist, the load will fail, but it won't matter as we can just go right into calling our drawScreen subroutine either way, and print out either the spaces that weren't overwritten by the load, or the strings that were in the file. We'll see what drawScreen looks like soon. But first we need to get into the main loop, which is going to be keyboard driven. So we start with a GETIN and keep calling it until it returns a non-zero character code. If A is loaded with Q, then we know the user wants to quit, so we branch to @quit. If GETIN returned an A, we branch to @enter A. B takes us to @enter B, and finally, if it's not C, we simply ignore it and go back to the beginning of the main loop. Otherwise, it was C, and we go ahead and load X with 15, which is the row of the C string. Then load the 0 page pointer with the address of the C string and branch unconditionally to @input. Then we see @enter A and @enter B, which do pretty much the same thing, except with the corresponding row indices and string addresses for the A and B strings. Finally, regardless of which string was selected, we fall to @input and load Y with 8, which will put the cursor 2 spaces past the expected colon when we call plot. We now want to use Y for indexing, so we initialize it with 0 and go into the input loop. There we call CHRIN, and if this is the first iteration, the cursor will start flashing and the user can start typing. Once they hit the return key, that first call to CHRIN will return, and the first character in the line buffer will be stored in A. If the character is the return character, we are at the end of the line buffer, so we branch to @redraw. Otherwise, we continue on and store the character in the string buffer using the 0 page pointer and doing an indirect store indexed with Y. We then increment y and check to see if we have read in 10 characters yet. If not, we go through the loop again and keep pulling characters out of the line buffer until we either see the return character code or fill up the string buffer with 10 characters. Once we are finished with the input loop, we fall to @redraw, where we call drawScreen again, and the screen will be fully refreshed before going back to the beginning of the main loop. Finally, the main part of the program ends with @quit, where we load up the 0 page pointer with the address of the first string, and then the pointer address is loaded into A. We load up X and Y with the @endstrings label address, which will give us exactly the address following the end of the last string, and we can finally call save before returning to the basic prompt. After the main part, we can define our drawScreen subroutine, which will first clear the screen by printing out the CLR control code. Then we call our printLine macro 3 times using the needed arguments for each of the 3 lines, and then we can return and our program is complete. We have a build script, of course, and all ready to assemble kernel.asm and link together kernel.prg to load into the emulator. It also generates a listing at kernel.list, and we'll take a look at that after we build. So let's go to the terminal. Let's call that build script, and now we can see that our directory contains both of those artifacts we are expecting. Let's take a look at that listing right now back in the editor. Here we can see the listing, and you will notice that the macro definition right down here, it's still there, but the address isn't changing, and there's no machine code getting printed out until jump start. Of course, that's how macros work, but if we scroll down to where we actually called it 3 times, there, we'll see the first 12 bytes of machine code that is generated for each of those calls. We can see by the addresses that each call takes up 36 bytes. So that's not too big to repeat 3 times, and using a macro looks like a good idea. So let's fire up the emulator and finally run this program. Here we see the emulator is in default 80x60 text mode, but when we load kernel.asm, or not ASM, PRG, and run it, we see the display clear and come back in 40x30 text mode with 2x zoomed characters. The ABC file doesn't exist yet, so all 3 strings are blank. Let's go ahead and press A. And there we see the cursor start blinking on the A line. Let's type something and hit return. And there it still is, but now the cursor is gone. If we hit C, we can type some more and hit return again. For good measure, let's put something in B. And now we have something in all 3 lines. Or almost something in 3 lines. Let's try going back to A and typing in more than 10 characters. Maybe we'll spell this one correctly. How about that? And then after we hit return, we see only those first 10 characters that were stored in our A string buffer. Everything seems to be how we want it, more or less, so let's hit Q and we'll get out of there. Now we're back at the basic prompt, so let's run it again. And now we see those values are still there since they were loaded from the ABC file. We could completely close down the emulator and get these strings back as long as the ABC file isn't changed or deleted. Let's go back to the text editor one more time and take a look at that file. We can see that header before the string start, which is a couple of funky characters that translate to the little endian address of the first string buffer in the X16 RAM. But then we see the 30 characters we are expecting, with spaces padding them to keep each string 10 characters long. So the total length of this file is 32 bytes, and when we run our program again, the 30-byte payload will be loaded back into memory right where it was last time. That's it for this lesson, but I strongly recommend you play around with this program. It really does a good job of illuminating how the basic line editor works and how you can use CHRIN to add that functionality to your own program. You can also try playing around with it by changing the string lengths or plotting them at different locations on the screen. And what happens when you type in a control code instead of a visible character? Do graphical characters work, and what do they look like when saved to a file? There's a lot to experiment with here. We still have a lot more to cover with the kernel, but we won't go through all of them at once like we did with the instructions. We have a lot of other things to cover, so we'll work our way around to some more of the fundamental programming areas next, including how to do more with Vera. If you don't want to miss any episodes in the future, make sure you subscribe to my channel and click the bell to get notified when they come out. If this episode taught you anything, please click the like button, and if you have any questions, please put them in the comments, and that can influence how future episodes are made. If you can't wait for the videos to go public, become a patron and get access to new videos as soon as possible, just like the folks you see here did on my Patreon page, which you will find linked in the description along with a GitHub repo containing all the materials for this tutorial series. Thanks for watching, and I hope to see you again soon. Bye-bye!